To go.
Right.
Good morning, everyone. Hope everybody's doing well today. So as we started with the last session, we're going to do a little bit of review from on what we took on session number 2, and then we'll continue on with some preliminary treatment and then into some clarification. Just a reminder, when you're prepping for the exams and when you're writing the exams, they're typically all multiple choice. You'll have 4 answers. You need to choose the best of the 4 answers. You need to keep in mind too that the answers may not be typically what you do in your region, but these exams that you're taking, I'm assuming from ABC, are all developed North America, and they try and make them as applicable as possible, but things may be a little bit different from region to region. So just remember to always pick the best answer. All right, I'm going to share my screen and we'll start with the review. Any questions before we get going? All right. Just want to bring up the chat box just in case any questions pop up. There we go. All right, so we've got several questions. Again, reviewing what we took in the last session. These review questions, as you're going through and studying, reviewing some of the webinars, taking the information, these review questions will help you prep you for those exams. Again, they're not written for the exam itself, but they are very typical of some of the questions that you might see. So we'll start with questions on some motors. What is a unit of measurement for the force of an electrical current? And again, I don't expect everybody to answer, but we're going to pause until we get somebody, a couple people typing in an answer on their keyboards. We'll try and make it as interactive as possible. A couple answers of amps. Actually, if you take a unit of force of an electrical current, it would be volts. What's the unit of measuring flow rate of an electrical current? Anybody got to try that? Yes, you can say amps now. It's just think about those two forces, volts, how much is being forced or pushed down that piece of wire, and the flow rate is amps. Okay, so how much is actually flowing, how much power is actually flowing in there. What's the unit for measuring electrical resistance? That's correct, ohms. Those 3, make sure you really understand those in preparation for your exam too. You don't have to be an electrician, but you do need to, there'll probably be something similar to that on your exams. What is the unit for measuring total power in an electrical circuit? That's right. So kilowatts, watts, depending on the size of power service that you're talking about. And describe Ohm's law triangle. Anybody want to take a stab at that one? Yeah, V equals I over R, or I times R. Okay. And describe a single phase alternating current. One answer there, it's not quite right. So the answer was alternating current divided by direct current, but we're just looking to describe a single phase current. So the current alternates, that should be 60, not 60, 670, 60 times per second, allows for transferring voltage and current typically used in homes and businesses. So the biggest kick there is the current travels in both directions and at 60 times per second. And describe the DC current. So the DC current is movement of electrons from negative to positive, and you need a closed circuit for the electrons to flow. So just like I said, we're not trying to be electricians, but just understand the alternating current moves at 60 times a second, travels in both directions. DC current is similar to your car battery, flows from negative to positive, and in order to, you have to have those two connected in order for that current path to flow. And describe three-phase alternating current. Anybody want to take a stab at that one? So it's similar to single phase, except there are three phases performing the same function. And with three phase, you're allowed higher voltages to run larger pieces of equipment. So a couple questions on motors and current. The answers I got back were close, but not exactly where they should be. So take a little bit of time and review that section. Okay. Yeah, what would you consider to be the most common motors found in a facility? Said you're gonna. That would be a light humming noise would be typically what you'd like to hear for sure. But what kind of motor? And those are three-phase AC motors. That's right. Thank you. We're going to move on to drives. A couple questions on drives. Can you explain how a belt drive is set up? What's a belt drive? So belt drive, if you remember from one of the graphics that was played, pulleys are installed in the pump and motor and connected by a belt. Okay. Very simple drive, but very effective in a lot of applications. What's a variable speed drive? So one of the answers is when a machine can ramp up and down easily. Fair enough. Again, it's not the makeup of VFDs or variable speed drives, but a clear understanding, which is what you have, which is used to vary the operating speed of equipment, which is perfect. Thank you. Where would a right angle drive be used? What kind of what application? Where do you think you'd see that? So vertically mounted equipment is connected to a horizontal motor is what it says in the text. So basically, if you have a pump that's mounted, a lot of motors are on top of the pumps, but if they're not, they'd be connected with a right angle drive to connect the motor to the pump. Hey, a couple questions on HVAC systems. What are some basic HVAC equipment? So heating and ventilation equipment. And I know there's a big long list, but just if you can throw a couple examples to me of what are some of the basic equipment? Anybody want to take a crack at a couple pieces of equipment? Air conditioning, yep. But so HVAC is heating and ventilation, to basically there to make life a little more comfortable from us. Consider, have your equipment in a well-maintained environment. Yeah, one of the answers is condensers, air handlers, compressors, you bet. Cooling units, fans, blowers, filters, those are all part of HVAC. What would you consider to be the most common HVAC system in facilities? Most facilities, most buildings, as you walk around, what's the most common type of HVAC that you'd see? Rooftop units. Yeah, one answer is central air. Typically the same type of units in a lot of cases, but most buildings will have a prepackaged rooftop unit. Units put in place, fans, condensers, coolers, filters, everything's in one unit, connected to the building, and away they go. Can you explain a geothermal system? Again, these questions are all just designed on the basic explanation of a system, not the details or in great detail, but if you were writing an exam and there was something, what could you explain a geothermal system? The answer, using ground temperature for heat. You betcha. That's exactly what it is. Water circulated through lines in the ground for heat transfer. And you can use it for heating or cooling. Perfect. Thank you. Moving on to cathodic protection. Can you explain corrosion? The basics of what's happening when pipes are corroding. So corrosion is a reaction between metallic pipe and its surroundings. That's when you get right down to it, that's the basics. Good answer, thank you, Nicole. Will cathodic protection eliminate corrosion? Any thoughts on that one? Yeah, that's right. Slows us down, reduces the probability, inhibits the corrosion. That's exactly right. Great answers, thank you. Can you basically explain how cathodic protection works? Couple tough questions first thing in the morning. Sorry about that. One answer is it's built into pumps. So answer that question, because there was a question mark on there. It's not typically built into a pump. It would be mainly designed to protect pipe that's in the ground, whether it be natural gas pipe, metal pipe for sewer works or water works. Typically a system that's put on afterwards. So some really good answers there. So basically, DC current is impressed into a metal pipe by means of a sacrificial piece or rectifier. Current flows away from the pipe. I had a few spelling mistakes on this. I didn't think this morning. I didn't do a spell check on it. Sorry about that. But really good answers there, and exactly right. It's driving the current from the pipe to a sacrificial piece, which draws everything away from the pipe, which then slows down or inhibits corrosion. How often should a cathodic protection system be inspected? Yearly, 6 months, every 60 days. It definitely depends on the system, but some all really good answers. Thank you everyone for chiming in. It's great to see the feedback there, and everybody's pretty close. It's a kind of a tough question when they ask about the whole system in general, but you would the sacrificial piece would be on an annual basis. Rectifier readings are recorded monthly, and so all really good answers. Thank you. Touch on just a couple questions on cross connections. What's the definition of a cross connection? And the answer I have here, when sewer meets the main water line. That's absolutely correct. You know, it's an actual or potential connection between potable and non-potable water. You define what potable water is. Yeah, good answer. Any drinking water supply. And can you define non-potable water? Basically, non-potable water is all other water sources. So if it's potable, it's drinking water, and non-potable is everything else. Good answers, thank you. What's the best practice to control cross connections? So if you wanted to do your best to control cross connections, what do you think one of the first things that you would do? air gaps, backflow preventions, labeling. Those are all really good answers to help with the system. And those would all be, you're exactly right, those would all be part of a cross-connection control program. What are two avenues for contaminants to enter a potable water supply via a cross-connection? So how can contaminants enter the potable water supply through a cross-connection? Leaks. Well, you could have a leak in the pipe in a potable water supply for sure. Yeah, but it has to get back in there. You betcha. Low pressures, back pressure siphonage. That's exactly right. You either have to have a higher pressure on the non-potable supply that's connected, or siphonage with lower pressure on the potable water. What are the two methods to control cross connections? We've touched on these already. So you can have two separate water supply or install a backflow preventer. Who's can work on a backflow devices? You got backflow set up in your plant, and you're going to be inspected and tested. And who's going to do that work? Yeah, you betcha. Certified technicians. Can you basically tell me what an air gap is? Physical space no less than an inch. You're exactly right. I wouldn't focus so much on the space as much as it's separated by physical distance. Good answers, thank you. And how does a backflow device work? So just flow only goes in one direction. Flow can only go one way. You betcha. Flow travels through the device in the intended direction. If the flow reverses, the flapper closes to prevent flow. Really good answers. Thank you. All right, so I'm going to stop sharing my screen while I switch over. The section we covered, that review, there's quite a few really good points in there, so make sure you review that one as well when you're cramming for the exam. Any questions on that before we continue on with the preliminary treatment? Okay, share my screen. So right at the end of the last session, we started on preliminary treatment. We talked about screenings, the most important parts of pre-treatment screenings, grit removal, comminution. And we finished up on comminutors. So we'll go through this section, and then I'll gladly answer any questions. If I'll try and keep an eye on the chat. So if something pops up, please let me know. All right, so the comminutors are bar meters, you know, they basically cut and grind material, making it smaller so it'll flow through equipment. Not in this picture. This would be a treatment facility. Cutters, you can see the blades on the machine which rotate. They pass through this attached cutter, and then any material is sliced from smaller pieces or larger pieces of smaller pieces. As we discussed, having those in a treatment plant, in my opinion, is not your best option. You're taking pieces of rag, and you're, instead of taking them in a bar screen or a plate screen type scenario and removing them, you're actually making them smaller so they can flow through. They will wind up wrapping around all kinds of pieces of equipment in your plant. The incredible reforming rag, it's amazing. Aeration systems are famous for having rags reformed in them. There is a really good application for from these type of equipment or grinder type pumps in a collection system. You would use, in a collection system, they're making the rags or pieces smaller so they move through the system. And like in our scenario, we have a 10 millimeter plate screen at the plant. So we have a lot of grinder pumps in our collection system. So making the pieces smaller, having them flow through the system, and then removing them at the plant works really well. Those grinders do not make the pieces smaller than 10 millimeters, so everything is removed at the plant itself. But not preferable just to have grinders in front of a wastewater plant without anything else. A lot of times they'll be put in place, and a lot of it is to you know, especially in a collection system, like I said, it works well, and it saves pulling pumps, operators having to deal with all this rags and whatnot. If you pull a pump in the field, you have to deal with these rags. You pull them out, and then what do you do with them? You load them in the back of a truck or take them somewhere. So some type of grinder or chopper pumps in the field can work really well. So grit removal. Sorry, I have to keep popping up my chat screen just to make sure, just see if anything pops up or comes up there. So bear with me. Grit removal. So grit's the heavy inorganic matter in wastewater. So sand, gravel, silt. When it's mixed, when that material is mixed with organic matter, it's known as detritus. I'd remember that term because you're probably going to see that on an exam or something similar. So basically, your initial grit removal system that contains inorganics and organics together is detritus. When you take grit and clean it or return the organics back to your waste stream, then what's left would just be considered grit. Grit removal is hugely important in the systems for removing that sand and gravel. It will cause immense wear and tear on pumps and mixers through your system. Not only that, is after a certain period of time, you'll have grit that'll be flowing through, because it's heavier, it'll flow through a tankage. And anywhere that it can settle out, it will, and it'll start building up in corners, and you actually will start reducing the volume of your tank after a while. So types of grit removal systems, we're going to talk about grit channels, aerated grit chambers, and mechanical grit separators. Just curious, what type of grit systems do you have in your facilities, if any? Do you have any grit systems in your facilities at all? Not seeing any in feedback there, so I'm going to have to. I'll have to assume either you don't or you're not sure, which is fine either way.
Hello, can
Hi.
you hear me? Hi.
Yes.
At our facility, we have a headworks, and on our headworks, we have like a grit classifier, grit cyclone, and a bar screen. So we do have a grit channel.
Oh, nice. Okay.
Yeah.
Cyclones are one of my favorites for sure. We'll talk about those. Thank you. So a grid channel, very simple design, look very similar to a rectangular primary clarifier. Grid channels they're solely designed to slow the influent flow down, so the grid has a chance to settle out. It's it's heavier than the water, and if the water is slowed down to the point where there isn't a lot of turbulence and the velocity is reasonable, the grid will settle out in the bottom. Aerated grid chambers, these work really well. Also, they're basically you're adding air to the system. Some facilities have an aerated grid chamber. If they have sewer systems that have a really long runtime, they'll put an aerated grid chamber in to kind of freshen that wastewater. It also, when you inject the air on one side of the tank, it causes a rolling motion in that tank. When the water and the grit hit in that rolling motion, when they hit the outside wall of that tank, it basically slows the flow down a little bit, so it gives a chance for the grit to settle out. I have a really good schematic of that coming up in a second. So the grit settles out on and then is removed by some kind of an auger system, and then the water carries through. So here's an aerated grit chamber. Like I said, you inject the air. You wouldn't want to inject too much air, or you're going to create so many turbulence that the grit remains suspended and will just carry right through the tank. But enough of the turbulence to drive the water and the grit in a rolling direction. Grit hits the wall, settles out, and then is removed by this screw conveyor or auger system at the bottom. Grit separators work in the same concept. It's changing the flow pattern that's coming in, allowing enough time for the grit to settle out. So in this type of system, the flow would be coming in, it would travel around the tank and then discharge through the other side of the channel. You've allowed the grit to settle out. It's like any centrifugal thing. You spin it, the heavier components are going to be flung to the outside, and when they are, the grit settles down in this tank, and then it's removed. They're typically, a lot of them will have some kind of a scraper system in here to keep the grit moving off the angled walls and allow it to settle out in the bottom. So ideally, you want your grit that comes from the plant, you remove it from whatever type of system, should be clean, so there's no organic matter. You need those organics back in your treatment facility to feed the microorganisms. And if you remove too many at the front, you're actually going to starve your microorganisms, which is going to give you grief down the road. Typically, a landfill will accept washed grit and screenings because they're classified as non-biological because they've been cleaned. In practice, you never achieve 100% cleaning, but the concept is that you send it through some kind of cleaning system and that it can be handled at the landfill. Talked about that already. So cleaning or washing of the grit is typically, if you've seen a system, thank you for the one answer, the comment about classifiers, which basically an auger type system. So when you've removed the grit, it gets pumped to a classifier, as the classifiers are built on an angle, as the auger inside the classifier turns, it slowly drags the grit up to the top so it can be disposed of, and it's washed at the same time. So typically, or in general, 1 meter cube of grit is removed for 40 million liters of wastewater. That's a typical design standard that is used. You may see that kind of question pop up as well. Any of your systems use pre-aeration tanks at all? Either type an answer or chime in on your mic. Just curious if you've dealt with any pre-aeration systems. The headwork sent to an SBRs. Okay. So the level 1 and 2 exams definitely cover the basics of treatment, preliminary treatment, primary treatment, and some secondary, and pre-aeration tanks will be on there for sure. So it's good to have a handler and understanding where they potentially could be used. So a lot of pre-aeration, as we talked about a couple slides back, can be used to freshen up septic wastewater. If you have systems that are very long, wastewater is tending to go septic, potentially you'd add a little bit of air there to freshen up before it hits your bioreactors or your SBR or an aeration tank. Pre-chlorination can be used as well. Big objectives there, if you want to do some odor control, change the sulfides, so you might want to protect your plant structures. It does aid in sedimentation a little bit and reduction of BOD. That reduction is all designed around keeping the wastewater fresh. You need to have it fresh so it gets to where the organisms can work on it effectively. There are a lot of other chemicals out there now that are used for odor control as opposed to chlorination or pre-chlorination. The biggest concern with pre-chlorination is chlorinating too much or over chlorination. So over chlorination, you'd kill anything that's alive in that waste stream. And typically you would then have a carryover of that chlorine into your biological reactor, which is then going to turn around and kill the microorganisms that are in there. So odor control, you can definitely use chlorine for that. There's some bioxide or any nitrate based chemical is a little easier for odor control without potentially causing harm to your system. One big thing about odor control too is if you can have bylaws in your system or oversee construction in your city or municipality to reduce or eliminate long-standing lines of sewage in pipes. Our bylaw, for example, states anything in a force main cannot sit there for longer than 45 minutes. So trying to keep everything moving rather than having development farther out, sits in the line, goes septic, which causes you odor concerns throughout your system, but also very detrimental to your treatment facility. Just looking for any questions.
Good question. What kind of gases are there in the odor? Is it just H2S or is there other gases as well?
The majority you're going to find in sewer systems are H2S. If you are dealing with discharge from industries, there may be other things in there as well, but hydrogen sulfide is the main one that you're going to see. You need to be, if you're dealing with odor control as well, and if you're adding a nitrate-based product such as bioxide, depending on your treatment system, you need to be really careful with that as well. We add a lot of bioxide throughout our collection system, but it's all at as minimal dose as possible. We have a BNR facility, which is designed to remove nitrates, which is really hard to do when you add nitrate to the beginning. So everything comes with a balance. It's a lot of non-professionals, well, we'll just throw some chlorine at it, or we'll throw another chemical at it, and all they're doing is creating problems, potentially more problems down the line. So everything needs to be done in a balance, and needs to be well thought out. Are you dealing with a lot of odor concerns or H2S concerns in your collection systems, which wind up reaching the plant? Or so with chlorine added at the front end of the plant, there will be some questions on what exactly is happening there. So chlorination wastewater, you're producing a small residual because you don't want to carry it through to your reactors, and that basically delays the BOD demand. So rather than there being a BOD demand in the system or at the head of the plant, and things start decomposing, which causes you problems, you're delaying that interaction, so you can get BOD demand happening in your bioreactors where the microorganisms are, which is what the system is designed for. Okay. So a lot of components on preliminary treatment. There's going to be, you can expect in our next session, there's going to be quite a few questions related to around that. It's hard to pick out exactly what you might see as you're prepping in this short period of time for a level 1 or 2 course, but I think we've hit the highlights of a lot of things that you typically see in preliminary treatment. So before we move on to our next section, any questions? All right, I'm going to share my screen. Bear with me while I get this organized. All right. Just waiting for the PowerPoint show. There we go. So we're going to move on to clarification. We're definitely getting in. We've covered in the first few sessions a lot of safety, cathodic protection, cross connection. Those safety is definitely part of everybody's job. Some of the other modules we covered may or may not directly affect your day-to-day job, things that you deal with. They will be on the exams. Spend some time, make sure you understand those things, some relatively easier questions if you read the material, and marks are important. As we do the review at the beginning of each session, I don't focus so much on whether somebody has the right or wrong answer as much as for you, you should focus. If you don't know that question off the top of your head, just highlight it so you can go back and review it a little bit more. In another 1 or 2 sessions, we will have, we'll start with some practice exams as well. And when you do those, the key focus again is not it's not, well, I got 70% on the practice exam, so that's good. It's not, it's more highlight the areas that you need to review a little bit more that you're unsure of. All right. So basically, the second step in the treatment process is primary treatment. Primary clarifiers remove about 61% of total suspended solids, and about 35% of BOD. Primary clarification is a similar concept to a grit removal system where you need to slow the velocity down. Sludge will settle to the bottom, and floatable material comes to the surface. Typical picture of a primary clarifier. There's many different designs, whether it be rectangular or circle, but they all perform the same function. In this schematic, you see the influent goes through your screen, through some grit removal, makes its way to the primary clarifiers. So sludge is off the bottom. In your systems, do you deal with digestion or fermentation, or what do you do with the solids off the bottom of your primary tanks? Just looking for a little bit of feedback on what do you do with the sludge from your primary tanks.
We dry off the tank and then we take it to field and spread it in the dirt.
Land application, that's definitely a good good use of it for sure. It's interesting when part of the reason I asked that question is depending on where operators are located has a lot to do with their what they do with sludge and settling. In Canada, where we are, you could do that kind of approach for a few months out of the year, but the rest of the year, with all the rain and snow, etc., it doesn't work really well. In drier climates, for sure, it's a great use of that. Would that plant there that you just explained, where it's taken to a dry bed, is that just a primary plant, or is that a secondary treatment of some sort?
It's a secondary biological plant.
Okay. So what's the purpose of primary treatment? Like I said, it removes, slows the flow down. You want to get the sludge off the bottom and the scum off the top. So in front of that, you have the screenings we talked about, grit channels that we talked about. And so into the functions of a primary clarifier. Okay, so settling rates. So basically with a primary clarifier, if you break it down, you've got the specific gravity of particles and how they're designed, how the clarifiers are designed is to allow typical particles to settle. The size and the shape of those particles is of great importance when you're designing clarifiers, and also the temperature of water. So warm water is less dense, which basically means the molecules in that water are spread apart a bit, which allows for easier settling or sedimentation. Depending on your level of science knowledge and whatnot, it's just one of the important things with that is like warm water floats on top of cold water. So if you were diving into a lake or something, you'd have the first few inches is warm, where then you get into the cold water. And the same thing works in a primary clarifier. Unfortunately, operators cannot control typically the temperature of the wastewater, so it is what it is, but it does have an importance on the settling characteristics of that clarifier. Most wastewater is anywhere from 4 to 25 degrees Celsius, depending on where you happen to be. In the winter, we drop down to 11 or 12 degrees Celsius. We have to change our operational paradigm or parameters between summer and winter. We have two different operating modes. In the summer, we're right around 22 degrees. Everything is working a lot better than in the winter. In the winter, we'll drop down to, like I said, 11 or 12. Dramatically changes how we have to operate the whole plant. We may put more primary clarifiers in service to handle what's coming in. You basically, as the water gets colder, you need more of whatever you're doing, whether it be primary clarification or biological reactors. You need more tankage, you need more microorganisms to do the same work that you could do with less tankage and less organisms, depending on the temperature. One of the key points on this slide is maximum water density is at 4 degrees. At temperatures less than 4 degrees, water density begins to decrease, and that's typically why ice floats on water. I'm assuming that you don't have to deal with a lot of snow and ice, which is probably pretty nice. But it is one of the things that colder weather climates have to deal with. A lot of times people don't think of water with viscosity. If you take motor oil, for example, it's very thick, much higher viscosity, but water and affected by temperature has a viscosity compound. That's usually in the clarifier design more so than operations, but it's just interesting to understand that a particle will settle faster in low viscosity water, which makes sense. If you threw something into a barrel of oil, it would probably sink, but it's going to float down really slowly, whereas you threw that same particle in water, it's going to sink a lot faster. So we also talked about not only primary clarifiers, not only settle the sludge out in the bottom, they want to slow things down enough so scum floats on top. Anything that you can remove in a primary clarifier, or the majority of it, you typically couldn't treat in your bioreactors. So if all your scum and sludge if you didn't have a primary clarifier, went right to, depending on your treatment system, but the majority of them goes to those plants, you're not going to be able to treat that. It's just going to wind up in your secondary clarifiers or flow right through to your effluent. So that's why you're trying to remove it at the front end. Flotation depends on specific gravity. Obviously, if something's heavier, it's not going to settle. Particle size and shape as well. If you can slow things down, some of these particles tend to, they form or clump together, and then they'll rise to the top. The primary clarifiers, you definitely don't want a lot of turbulence. So if you are experiencing turbulence in your primary clarifiers, hopefully you have another clarifier that you can add into service. Flow currents are huge. They're not a lot of things that are overlooked sometimes. Influent to your clarifier needs to be a well dispersed pattern, whether it's a rectangular clarifier, so it's be dispersed at one end as it moves through, or a circular clarifier, typically have a ring in the center, and we'll talk more about those in a minute, which disperses the flow around the tank. Sludge buildup is huge, not only for unsightly or anaerobic conditions, but it does reduce the footprint of your tankage. So if you're not having adequate sludge removal, it's building up in the corners, building up on the sides or on the bottom of the tank, and it's actually changing the volume of your tank. Just checking the questions. All right. So sizing clarifiers, clarifiers, primary clarifier has been in use for a long time. One of the first treatment plants in our area, for our city, was, if we have pictures on the wall from back in, I think it was 1913 or something like that, and it was primary plant. Primary plant, some solids were handled, either drying beds or incinerators, and then it flowed to our lake. Okay. The three things we're going to talk about next with primary clarifiers are detention time, rise rate, and weir overflow rate. A lot of those come into when design of primary clarifiers. So that's where most of those terms come in, but it also makes a crucial operating factor, especially detention time. The rise rate we'll talk about that in a minute, but that's more what's happening when systems are designed, and the same with the weir overflow rate. But your detention time is something that is 100% in your control. So the explanation of detention time is the average length of time wastewater is in the clarifier. So basically, from when a drop of water enters that clarifier, how long it takes it to leave. If your detention time's too long, you're going to start decomposition in the tanks. If it's too short, you're going to force things right through the primary tank and then out into your reactors or biological tanks. Pretty simple calculation. So detention time is the volume of the clarifier divided by the flow. Do you, in your systems with your primary clarifiers, I'm hoping you have multiple tanks. Do you take them in and out of service based on operational need, or is it pretty much a set parameter and you just run the primaries that you have? I'm just curious about that. Anybody? No comments on primary clarifiers? All right. So the rise rate, like I said, most of that is done by engineering firms when they design your clarifiers, but I just wanted to make sure that you see the calculation. You wouldn't typically use this calculation for operations, but it's important to understand what's actually happening with the rise rate when they talk about it. So in clarifier design, rise rates, one of the most important factors. Low rates give better solids removal, for sure. So basically, they're saying most clarifiers are designed between a rise rate range of anywhere from 10 to 50 meters per day. The low rise rates are usually used in small plants operating in colder climates. So basically, a smaller plant, colder climate, you need more lower rise rate, which is less flow through the tank, so you can get those things to settle out. There will be a question, I would assume, on rise rates. Okay, just to better, or just to make sure you have an understanding of what exactly is happening there. Weir loading rate, so it's length of effluent weir in relation to the flow. How much flow is going through your tank against the weir, whether it be a sawtooth weir or a different type of weir system. At your facilities, your primary tanks, are they typically sawtooth weirs or underflow baffle weir system? What kind of systems or what kind of weirs do you have in your primary clarifiers?
Sawtooth.
Sawtooth weirs, yeah. Probably on your secondary clarifiers as well. They're typically used everywhere. In these this online training. It's a little hard to go through all the calculations, but just take a minute, take a look at this calculation for WEIR loading rates. It's pretty basic calculation. I would think you're going to see something similar to this on exams. Again, you do have calculation sheets that are provided through the exam, but WEIR loading rate is basically the flow divided by the length of WEIR. So if it's a rectangular tank, it's very easy to figure out the length of that WEIR with a measurement. Circular tank, same thing. You just need to do the calculations to take that circular into a length that you can divide the flow by. A couple examples of primary clarifiers. So rectangular clarifiers, circular clarifiers doing the exact same thing. Okay. Just take a second on the slides here. Okay. So your primary clarifier, whether it's circular or rectangular, like I said, they do the exact same thing. A lot of plants have a primary clarifier, it's circular, and it looks very much or almost identical to a secondary clarifier. We'll take a couple minutes here, just talk about the different zones, and then we'll take a bio break in a minute here. So any clarifier, you have your inlet zone. So that's how the flow is getting into that tank. Your outlet zone, typically going across sawtooth weirs that we were talking about. Then you have a settling zone and the sludge zone. So if you were asked on an exam, what are the 4 zones of a primary clarifier? Those are the types of answers that they're looking for. Parts of a clarifier, so you have the influent, the drive, and the motor. That's in this example, that's a good example of a right angle drive. The vessel is the tankage itself, sludge hopper at the bottom, sludge line for removal. And this one that's cut off on what's cut off of my screen anyhow is basically talking about the sludge rake mechanism. Oh, there we go. And your baffle tube, which is in the center, which disperses the flow. So in a circular clarifier, there'll be notches in this baffle tube a lot of times. Sometimes this baffle tube is just at the just below the water level, which allows it to flow that way, depending on the design. This is the last slide we're going to take a look at quick before we take a bio break. It's about 10 after 6 my time. So basically, sludge comes in, it's dispersed through the inlet zones, dispersed through the tank. We got slows the flow down your primary clarifier. Sludge is going out the bottom, and clearer or cleaner water is going out the top. If it's a primary tank, that effluent might just go through some kind of disinfection, then go directly to an outlet source. For a secondary treatment plant, it's now from the primary clarifier full of contaminants is being fed to your secondary treatment. Before we take a quick break, any questions on that part of circular clarifiers? Okay, why don't we take a quick 5-minute break? Everybody can top up their coffee, and then we'll be back.
Okay, 5 minutes break. Pause for a cause. Okay, Mike, we're back.
So great, thank you. Hope everybody had a chance to fill up your coffee. I know I did. It's early in the morning here, but that's okay. I like to start early and get things accomplished. I know some of this stuff is, especially in the primary treatment, is a lot of review, a lot of things you probably take for granted in your day-to-day jobs already. There are some things, make sure as we go through that, yeah, I'm pretty sure you understand how a primary clarifier works. But when you write an exam and stuff, you're going to, things like the zones, whether the 4 zones, that kind of thing are definitely going to appear. I'm going to share my screen. So we just finished talking about the process flow. I'm going to look at the sludge rakes just for a second. There we go. So basically, the rakes are angled in a circular clarifier to push the sludge towards the hopper. Rectangular clarifiers have a chain and flight mechanism. And the circular clarifiers we're talking about now, as the influent comes in the center, sludge settles all the way through this clarifier, and so it needs to be brought in with the rakes to the center and removed. Just a good graphic. I'm assuming the graphic's working on your end, and you can see the and the mechanism turning around. So just review just make sure you understand the different zones of a clarifier, what's happening in those clarifiers. A little bit later this morning, we'll talk about typical maintenance and some of the things that can happen in primary clarifier. I just wanted to go through the design and exactly what's happening in that clarifier. So rectangular clarifiers, the same concept as a circular clarifier, except you have a chain and flight mechanism. Sludge settles to the bottom. It's dragged along the bottom of the tank to this hopper, and a sludge removal system removes it. Scum forms on the top, and then you've got typically a manual system to remove scum several times a day. So there would be a WEIR that's stopping the scum from flowing. If you don't clear your scum off regularly, you're going to have a buildup in scum. It's going to, it's even possibly, as this chain of flight moves around, it's going to drag it down to the tank, and it's going to scum's going to want to make its way to the top. So if it gets dragged down here, it's just going to go under this effluent WEIR and make its way to your system. So it's really good to make sure you clean that regularly. Let's bring up try and bring up the chat section. Hang on a second. Having a little bit of trouble. Just bear with me. I'm going to have to reshare my screen. I can't get the chat section to pop up here. There we go. Excuse me, sorry about that. Technology is wonderful when it works like it's supposed to. So currents in a clarifier, a few different ones that occur. So you have surface clarifier or surface currents for clarifiers that are not covered. That can, depending on your location and the wind direction and stuff, that can directly affect primary clarifiers and the scum that's building on the top. In a windstorm, it could potentially, cause enough surface current to remix that scum back into the water. Density currents, different solids concentration, and the wastewater temperature that we talked about. Not a lot that you can control on that. And hydraulic characteristics of a clarifier. So when they talk about flow patterns and hydraulic characteristics, they're basically saying removal rates in that clarifier and how you would attack that. So you can take clarifiers either in or out of service to change the length of time the hydraulic loading has on that clarifiers or on those clarifiers. A really good picture of a rectangular clarifier, and you'll notice the inlet zones. And why these structures are here is to change the pattern of flow through that clarifier. So as the inlet comes through here, these gates, you don't just have a flow of water flowing through the tank and then dispersing a little bit. It actually hits that baffle, changes the direction of flow. You'll have two baffles, two influent tanks, or two influents hopefully, and it changes the direction of flow and disperses it through the tank immediately. So you have a primary clarifier functioning at this end of the tank. It starts to function, rather than if you didn't have those baffles, there's quite possibility it's not even, the primary clarifier isn't going to function properly until the flow subsides a little bit from the influent, and then starts doing what it needs to do. And your systems, do you deal with circular or rectangular clarifiers? Primaries. Just waiting for a couple answers to see if I'm curious what kind of tankage that you have. Circular, rectangular.
Circular.
Okay. Anybody deal with rectangular clarifiers? So I don't hear any answers on that. So make sure you really take a few minutes and review the rectangular clarifier section. We talked about the outlet system with sawtooth weirs. These can be on rectangular or circular clarifiers. It's a good picture just showing chain and flight mechanism. Scum's removed on top, the chain comes around, the flights moves to the bottom, drag the sludge to the other end. There's your scum trough, typically operated manually at least once a day to remove the scum. Flow travels under this wall and then over the sawtooth weir, and this would be your effluent channel going to your biological tank. So some of the daily work that operators need to do, you guys do inspection, clean up, potentially some preventative maintenance, definitely some record keeping, maybe even some sampling for lab analysis, sludge and scum removal. So the visual inspection, and if your tanks are covered, you need to open the lids up every day and take a look at them. Sometimes it's easy just to walk by them if they're covered and not pay attention to them, but it's important to take a look. Typically the motors or some of the drives may be inside the covers, so you need to pop that cover so you can take a look, see what's happening. You want to look at the influent and the effluent sides of the tank. Influent is typically where your drives are going to be, so you want to take a look at that. Like I said, the effluent, you want to see what's happening by your effluent weirs, how the flow patterns are and what's happening there. If it's a covered tank, the middle of the tank isn't so, you wouldn't have to necessarily pull the covers and take a look all through the tank, because you can see the chain and flight mechanism from the influent side as you pop the cover and take a look there. Clean up. This is obviously a very big tank, but they need to be cleaned. On the smaller tanks, you want to do your scum removal at least once a day and your inspection at least once a day. I'm not sure the size of your facilities and whether you have millwrights or mechanical staff, but most operation staff are required to do some kind of preventative maintenance, whether it be greasing or just general inspection. Maybe even shear pins need to be replaced. Preventative maintenance is huge. It will not only protect the equipment that's there, it'll also increase the life expectancy. We have raw influent pumps, for example, that are probably 20 years past their life expectancy because they're serviced every year. The parts are still readily available, and rather than just running it till it fails, we do a lot of preventative maintenance on it. Do you have preventative maintenance programs in your plants? And if you do, are operators performing some of that preventative maintenance, or is it done by a maintenance staff?
So at our plant, hello, can you hear me?
Yep, you
Yeah.
bet.
At our plant, we recently just started backup maintenance coordinator. That's the program we use, and our operators do the maintenance for our plants, including exercising valves, looking at different equipment monthly, annually, and yearly. I mean, annually and semi-annually.
Oh, cool. It's I think some of the larger facilities you run into, operation staff don't typically get involved in any of the maintenance. And I think to be a really good operator, you need to have a really good understanding of how something works in order so you can monitor that operation and keep things going. So if there's ever an opportunity to be involved in some of that maintenance, I would definitely jump on that. Sometimes it's very separate in a unionized environment or other things you're not allowed to, but I think it helps an operator overall. Okay, so some sampling and analysis. Okay, so different types of pollutants with definitely different environmental impacts. Class 1, easily degradable, and we'll cover these a little bit in the slides coming up. Class 2 is toxic but non-cumulative. And class 3 are pollutants that are toxic and have a cumulative action. So examples of class 1, you temperature, color, dissolved solids, suspended solids, sediment, BOD. Class 2 examples, aluminum, iron, magnesium. Some things, phosphates, some things you can do nothing about. But the biggest difference, or one thing to remember with class 2, is they're non-cumulative. And class 3 would be obviously toxic, but they're cumulative. And there will be some questions related to these on those exams too. So a lot of them, arsenic, chrome, mercury, lead. Obviously pesticides, that's an easier one, but chrome, mercury, lead, and arsenic are ones to keep in mind for sure. And cumulative is they're building up in your system or in the ecosystem, so it doesn't degrade like other components, and they just you have arsenic there, it just keeps adding and adding and building up until you have a real problem. This is an overall guide for the primary clarifiers. Gives you typical ranges. Ones that I would focus here are BOD and suspended solids. There may be even something related to dissolved oxygen levels in a primary clarifier. It's important to note as well the removal efficiencies. Settable solids are 90 to 99%. Suspended are 40 to 60. Total solids are 10 to 15%. BOD, depending on the design and of the clarifier and your influent, is anywhere from 20 to 50%. And of course, when you remove all these things, you're removing some of the bacteria as well. So 25 to 75% of those. And just looking, yes, the answer, Nicole. If I can see, my chat box keeps going in and out, so I'm trying to glance at it as much as I can. Does anybody know what this gentleman's doing?
Sludge judge. Is it the sludge judge test?
You betcha. Not typically done on a primary, but it can be. For our primary clarifiers, sludge removal is all on a timed operation. So our PLCs tell the pumps to turn on and which valves to open and remove sludge. Operations staff for us, we've installed a clear piece of pipe on the discharge side of the sludge pump. And part of the operations staff is they go down there and they take a quick look to see the sludge that's flowing through that clear piece of pipe. It's very handy to show a quick glance. You can see the amount of sludge being withdrawn. You can see how long your valves actually stay open, because you only need to remove sludge through a hopper when there's sludge present. So if your timer is, and we adjust those timers accordingly, so they might go 5-minute run time per hopper, maybe different types of time of year, they might go to 7 minutes, because we're trying to remove the sludge without removing too much of the primary water itself. What would be the first indication that you have a sludge problem in your primary clarifier? So something's not working right in your primary clarifier, your sludge isn't being removed, what's going to happen? Rising sludge, you bet. And then following that, you're going to have enough sludge built up in there that it's going to cause you problems in your primary clarifiers, and you could well be breaking shear pins would typically be the first thing to go between the drive and the chain. That's kind of the sacrificial piece, letting you know that there's a problem in that clarifier. I have seen locations where the shear pins keep breaking, so they put in larger shear pins, or we'll just throw a bolt in there to keep things going. But people are avoiding the problem or potentially causing more grief by making those systems run when something is dragging. A piece of a shoe off one of the flights might be a problem. You got a flight that's dragging or broken free from the chain, and so when there's a problem and you have continual issues, you need to take that tank out of service and drop it to level down, clean it out, and see what's going on in there. Most primary clarifiers have a solids content about 5%. 5% is quite viscous, and it's sometimes difficult to pump. So you want to maintain your removal rates at something that's removing as much sludge as you can when the pump's running, but also not so thick that you can't pump it. Earlier, a gentleman mentioned that the sludge from the primary clarifiers is taken directly for land disposal or drying. Do you happen to know what percentage that sludge is at?
No.
So if it's really watery, it might be anywhere around 3% or so. A little thicker would be about 5%. If you're taking it for drying, that can be a tricky situation sometimes as well. You don't want it so thick that you can't pump it, but you don't want it so thin that you're just putting water in your drying beds. So that needs to be maintained and analyzed as well. Excuse me. Scum removal. Again, this is scum removal is typically done at least on a daily basis. A lot of times it's a manual operation. Pretty straightforward. I'm assuming that that you, as operators who are removing the scum from your primary clarifiers. I'm not sure if you've heard the term sludge coning. So basically what happens is it starts drawing down the center of this clarifier. So you've got the sludge buildup here. you might hear the term coning or rat holing, but you're basically drawing through the center of this clarifier. So now your flow is going in this direction. You're not removing any sludge from there. Excuse me. This can happen definitely if you have a rake or a removal mechanism failure, or even if the pumping rates are too high. So if you're trying to remove this sludge and it's trying to, it will follow the easy, water's going to follow the easiest path. So if you're pumping at 5 times the rate through your withdrawal system, you're gonna have coning or rat holing in your clarifier. Just a couple common causes, the last slide on primary treatment, but couple common causes of primary failures: sludge not removed often enough, poor equipment maintenance, lack of appreciation for the importance of lab tests, and failure to recognize mechanical or electrical problems. So any questions on primary clarification? There will be definitely quite a few questions related to primaries on your exams. All right, I'm going to switch PowerPoints here, so bear with me for a minute. Okay, we're going to move along for touch on trickling filters this morning. Do you, any of your areas, do you deal with trickling filters? It helps me understand how much, like these things will be on the exams for sure. So I'm just kind of curious when I ask these questions. I'm just saying thanks, Nicole. Just really need to know how much time to spend on them. If nobody has seen a trickling filter before, then we need to spend a little more time on it to make sure you have a really clear understanding. The last session or section, I have a lot of feedback on primary clarifiers. So we hit the highlights of primary clarifiers because everybody has those, and they, typically everybody understands that operation. So we just focused on more of the highlights. So trickling filters, I'm hearing no for a lot of, so thank you for that, because it helps guide me on how much detail or explanation that I need to provide. So trickling filters, and they work really well, depending on their application. I've seen trickling filters for different resort type facilities, whether it be a ski resort or other facilities, and they work well. And we'll dive right into on how they're designed, how they're operated, and what kind of maintenance is required. Excuse me. So most trickling filters are large diameter, shallow structures filled with stone and have an overhead distributor. So basically what they're saying is, and they're typically covered as well. You'll see a lot of applications in colder weather where they're covered, and in warmer weather, it's not so important. But they're saying they're very large tanks in diameter, shallow, so they're not too deep. And then the distributor on top, the distributor arm as it moves around. And I have several other pictures of these that we'll go through. So if this one's a little unclear, just bear with it. So the distributor on the top of this, so as this arm moves around, the wastewater flow is being distributed through all this media. Okay. So a trickling filter consists of three parts. You have the media, the under drain system, and the distribution system. So filter media can be several different designs. Any of these plastic type systems are mainly designed to give you more surface area rather than just a round piece of plastic. If you have one like this that has cutaways that allows flow in the center, you can promote growth on the outside and the inside of this media. So you're basically doubling the size of your growth area. The under drain system, trickling filter has a sloping bottom, and the under drain system is mainly there to support the filter media and permits airflow. So as the arm moves around and is distributing wastewater around the tankage, flows through the media, biological slime or growth living on the media needs air, which is picked up from the flow of the water onto the tank. There may be an air pump in some systems, but typically they don't have that. They're designed to be simply operated. Excuse me. And like I said, the under drain system supports the media, and that's a really key point. So the distribution arm or distributor system, typically they're rotary type. So you have, as we went through this slide, there would be two arms on either side of this drive. Flow comes in the center, distributed, kind of like you might want to think of it as a secondary clarifier, except you're distributing flow through this arm. Flows through whatever type of media. You have biogrowth on this media, which is living off what's in the wastewater. Air is picked up from this water as it goes from the arm and drops onto the media. Under drain system is supporting that media and allowing for airflow. So basically the under drain system is not letting this media pack on the ground, and it's letting air flow through the whole system. And then the outlet, as the flow moves down, it just drains out the bottom of the tank through an outlet system. Just trying to find a good picture for you. So this is the distribution system I was just talking about. So as this arm moves around, it's distributing the flow around throughout the tank. It's picking up O2 as it's dropping from this distribution arm onto the media. Okay. This media, like we talked about, could be a plastic type media, could be a rock formation, anything that will support that media growth. It's interesting. This would be your little walkway out to take a look on it, and it's just supported right on top of that media. They talk about fixed nozzle distribution systems, not as common as the rotary type. So the one we just looked at would be a rotary type system. So as this moves around, you're getting even distribution through that whole trickling filter. Fixed nozzle spray systems, or you're going to have nozzles maybe at either end or throughout the tank, and then you're hoping, or the design is to get as even flow as possible through these fixed systems. Any of my experience has always been the rotating systems work a lot better for distributing flow through the tanks. So some of the, the nozzles on the surface, a good way to think of it is like a lawn sprinkler, right? So the water flows through, pushes this ball or this fixed wedge out of the way and allows for the wastewater to flow where it needs to go. When the flows stop, then these orifices will drop down and close off that line so you don't have anything flowing backwards. This would be an example of a fixed nozzle system throughout the tank. Some of the problems with a fixed nozzle system, if you had one or two of these nozzles that were plugged, number one, they're hard to get at, hard to work on. But now you have a very large zone potentially in this tank that's not getting any wastewater feed. And they're all biological tanks, so it's exactly the same as an activated sludge facility or an SBR or any other type of facility. If you have no flow here, which means you have no food and you have no O2, this area is going to start decomposing and you will have sludge issues or odor issues being caused here. When typically with the central rotating dispersion systems, most of the problems there with plugging are easily fixed. If we go back to this picture here, if one of these nozzles was plugged, you'd just walk out here, wait till the thing came around, walk out here when it's turned off, and clean that nozzle system. Much easier for maintenance, much easier to get at. Okay. Excuse me. Ventilation is key for these units. If trickling filters, if they don't have proper air, a lot of them have the natural ventilation. Some is forced air ventilation, so they would force air up through the bottom of the tank to feed that biomass. Without air, it's exactly the same thing that's going to happen in any other tanks. You're going to have sludge buildup. It's going to start decomposing, which is going to cause you a lot of grief. A few more slides on trickling filters, but any questions so far? You'll notice that as we move along, any of the systems we talk about, they're all biological. So when you're writing an exam and there's if you understand, for example, a trickling filter, if it has how the water gets in there, it's got a biomass that's living off that wastewater. It needs air to live as well. It's the same. You can relate that back to any of the plants that you operate. So even if you're not sure of how a system entirely functions, if you think about any biological system needs the exact same components, whether it be a trickling filter, SBR, a BNR plant, it's all designed, the basis is the same, and then it just varies from there. So BNR plant, if you stripped off some of the things that are removing phosphorus and nitrogen, you just have a mixed liquor tank. There's absolutely no difference. The flow patterns and mixing in the tank are set up for BNR, but if you removed all that away, you'd have an aeration tank, mixed liquor, typical secondary treatment plant. So try and keep that in mind when you're looking at things, especially with trickling filters where it sounds like nobody's has any dealings with them. You haven't seen them before. It's just a biological tank that needs somewhere for the media to grow, so you have a biofilm on it. It needs food and it needs air. So rock media contains about 35% void space. Trickling filters with plastic media, like I said, you're basically increasing that space. You're also increasing the void spaces because those round or rectangular or cylindrical units, they're not going to line up side by side. They're going to be all mismatched. So you have got lots of really good space, and you've increased your biomass area for growth. So with any of these fixed growth systems, there's going to be continual sloughing of this that biomass. So as it gets a little older, it's basically getting heavier, and it's going to slough off a bit, and you need to be able to remove that. And it's important that that happens so you have new growth continually happening all the way along. If you can prevent ponding on a trickling filter. Ponding is basically where the or the filter media, whether it be the rock or the plastic, is getting blinded off somehow. And so you're basically ponding, so you have water that's forming on that tank somewhere. So if you can think of that biofilter as part of that, if it was rock media, it was blinded off, and there was no flow going through there. As the arm goes around the top and it's distributing water, it's going to pond on top of that water. So that shows you that immediately that there's a problem with your media. You're not getting any ventilation through that area of the tank whatsoever. You'll get questions on different types of trickling filters. So standard rate, high rate, or roughing filters. Standard rate filters would be, typically that's your form of treatment for a municipality or a ski resort or something like that. High rate, you might be using these trickling filters so they can process as much flow as possible, maybe in a pre-treatment type facility. And roughing filters would be considered the same thing, more of they're trying to take the initial load off that system or off that wastewater before it flows somewhere else. Filter staging. So you have single stage, which is basically one filter. Two stage, they can either run in series or in parallel. And if they're running in series, you have, it's like a primary filter and a secondary filter. So the first filter would be taking most of the loading. The settings would be a little bit different between the primary and the secondary filter. The secondary filter would then be finishing up treatment and a little bit of polishing on the wastewater. If they're running in parallel, it's basically two systems side by side, and they both get the same loading, same treatment level, and you have the ability to take one of those tanks out of service if needed. Hydraulic loading on a trickling filter basically expressed in meters cubed per day per meter squared of filter media. And then you'll have, like I said, if there's a math question on your exam asking you to what's the hydraulic loading applied to this filter, just take time, find your in your equation sheet, find this equation. So like I said, it's meters cubed per day divided by the meter square of the filter media. Organic loading, same as any organic loading in any other types of biological plants that you deal with. Because we're dealing with filter media and that kind of tank, so it's BOD applied per day in kilograms divided by the meters cubed. So the amount applied divided by the size of the filter rate. Gets into a little more detail on standard rate filters, hydraulic loading rates, organic loading rates. The key points to remember with standard filter, usually rock, depth of media with a depth of 2 to 3 meters. Again, preferred with the rotating distributor. Key point here as well with the standard rate filter. So if you think if it's in your system, your diurnal flows are going to be typically higher in the morning, then they slow down a bit, and then in the early evening they pick up again as everybody gets home, and then overnight they typically slow down. So a lot of these standard rate filters will have some kind of recirculation, so we can continue to feed the microorganisms in that filter media in lower flows. Same kind of concept if you were if you have equalization tanks in your systems. It's the same idea. So you bleed off a little bit of flow on the higher flow rates and then into an EQ tank, and then you slowly bleed some of that flow back in to continually feed your biomass. And you're basically, you want to keep your biomass alive and healthy so they can handle the higher flows when that diurnal flow picks up. So high rate filters, we talked quite a bit about those already. I just want to make mention that the media is 1 to 1.5 meters in, or with rock and synthetics is 4.5 to 9 meters. So why would that rock media that high rate filter with rock media, why would it have such a difference in meter depth? So the rock is only 1 to 1.5, and synthetic media is 4.5 to 9 meters. So that's a huge difference. Why do you think that they have that difference between the two medias and in that trickling filter? Any thoughts on that? If we want to take a guess at it, it's not a highly technical question, or it's not a technical question that you might think of. So basically your distance of space between the media with rock is a lot less than the synthetic media, like we talked about. So keep that one in mind. So with the rock media, you have to have less of that media in place, whereas synthetic media, because you have a larger area for the media growth, you have more area for the airflow to pass through, so you can have a much higher depth of media. Roughing filters. You're definitely going to see questions related to roughing filters as well. Basically, like we talked about, is high rate filter. It's receiving a very high organic loading rate. Like I mentioned, it's mainly used to reduce the primary or organic load. So if you typically, and maybe a fruit industry or some other kind of industry needed to shave off that organic load before it went into the wastewater system, you could have a trickling filter in there. So it's just shaving off the high rate, or the roughing filter is just hitting the peak of that treatment, so you can then discharge it to a sewer system. If you didn't, in the example I provided with fruit processing plant or a packaging plant, if you didn't have some kind of pre-treatment, whether it be a trickling filter, for example, that organic load hitting the system will basically overload your biological process. So you need something to take that load off in the first place. Filter staging, excuse me. So there are areas that that's their sole treatment, is a trickling filter. So they have a primary clarifier, secondary clarifier, and their biological treatment is a trickling filter. Typically very low maintenance. They run really well. They definitely prefer to have a constant, even loading rate. And we talked about the recirculation line, which is important to keep feeding that filter during low flow rates. I'm just going to talk a couple minutes on filter staging. Excuse me. So we talked about running in series and parallel. These ones would be running typically in parallel, right? So you could take this trickling filter out of service and it would run through to this trickling filter. In series, you'd have this trickling filter is getting more of the loading at the beginning, and then the secondary filter would be hitting some of the, or this would be like your roughing filter and then your standard rate filter, for example. Depending on the systems, your recirculation lines vary in location as well. This one, for example, it's taking the recirculation rate right off the effluent and bringing it back to the beginning of the whole trickling filter process. This type of recirculation line would actually allow you to take this first trickling filter out of service, because now it's fully designed that you can take that out, have the flow come around, and you can still recirculate. Whereas this one, if you didn't have that other recirculation line, you couldn't take just one of these out of service. You'd have to take them both out. So distribution and location of recirc lines can be critical as well. So just before we get into sampling on trickling filters and stuff, which will be the last little section we talk about today, as answered, people don't, or this group is not typically dealing with any trickling filters. Any questions so far? Hopefully I've explained it well enough. If you have, if you got some questions, please just type them as I'm talking right now. Just remember they're a biological treatment. So it needs food, air, as constant flow as possible is a benefit. Food is taken from the wastewater, air is taken from injecting air through the system, or it's picked up as the water drops off the arms, as it drops on top of the trickling filter. Recirculation to help provide constant feeding in low flows. Really remember the three different types of trickling filters: standard and roughing filters, the difference between those two. Any questions so far? Okay. I can guarantee you that you will see questions on trickling filters on your exams. Okay. So trickling filter is a biological treatment unit, and loadings and fishings are determined by the influent characteristics. Okay, much like any other biological system. So some of the testing, excuse me, some of the testing that you're commonly going to do, you want to do your BOD for the strength of wastewater. You want to know what the trickling filter is affected by the characteristics of the water that's being supplied, the weather, whether you need to cover it or not cover it. Industrial wastes and shock loads are very detrimental to these systems. So the question is, how is the filter operated during the winter time? Typically in colder weather climates, they will be covered. Not a cover that's sealed, but a cover, or more like a how can I explain this? Just a suspended cover or a roof over the tank. They're operated exactly the same, but that way you're keeping the snow, rain, and everything out of that filter with a suspended roof. The flow is going to be slowed down in the winter because your biological activity in that filter media, although you've got a good media, a good biomass, as the temperature drops, just like any biological plant, you need more time to do the same work. So, yeah, for example, there was one that we used to operate at a ski hill, and so it's out in the cold. It was covered. It worked really well. Unfortunately, that one you could see the difference because there is no equalization tank or no way to stop the high loads or high flows coming in. So that filter, although it did work well, there were certain areas, as there was a lot of people there, the flows coming in, you're actually washing out part of that filter and pushing that biomass right through. So you could see there were parts of that filter were forever regrowing all the time, trying to get that biomass. So luckily enough, as the flow came through, it dispersed through that line and it hit the outside of the dispersion ring. So we used to lose a little bit of biomass on the outside, but the inside was still operating really well. All right. Just some typical numbers, and these graphs are not so much for you to memorize. Like, this isn't a memorization exercise, but just I talk a lot about different types of processes and how they relate to other types of processes, because they're all, the foundation is all the same. Like I said, this is a trickling filter we're talking about, but it's a biological unit. And so you got dissolved oxygen that needs to be added, suspended solids. pH is the pH effect on a trickling filter is the same as a pH effect on a SBR, which is the same as pH effect on a BNR plant. They're all the same concept, and it's really important to keep that in mind. Some of the typical lab results, you want to just make sure you have an understanding of this and these ranges, because you'll probably see something on the exam. You know, if your trickling filter is having a suspended solids in the final effluent that's 200 milligrams per liter, what's happening in that unit, you know, which leads you to obviously that the biomass is gone, part of that growth is gone, the flow is just running right through the plant. In these numbers, if you have an influent of 150 to 400 and an effluent of 150 to 400, that filter's doing nothing. That's basically what it's trying to say. Okay. Some of the chlorine residual on the final effluent. Obviously, you want to, you know, it's going to chlorinate or disinfect somehow before it leaves that facility. Coliform bacteria and some clarity NTU results on those clarifiers as well. Or sorry, not clarifiers, trickling filters. The next section we're going to get into is activated sludge, which we're going to start next week. It's really diving into the process part of this course. There'll be a lot of time spent on that. We're going to slow things down. I'll be asking you a lot of questions as we get to that, for sure. Up and today we talked about, you know, the primary clarifiers, trickling filters. Any questions on those so far? It's we're about 20 minutes early, but I didn't want to dive into the activated sludge part until I wanted that fresh as one complete unit next time. Any questions on what we've covered today at all? You can be guaranteed on next Thursday morning, there's going to be quite a few review questions. It's very important about the trickling filters and the clarifiers. Level 1 and 2 exams are mainly centered around the basics of treatment, right? That's the entry level. You may not be at that level. You might, it sounds like you're operating facilities that are far above like a primary treatment plant. But the exams themselves are based on level 1 and 2. I think everybody said at the beginning, if I remember correctly, everybody's going for a level 1 exam. I would like to think that if you're operating a higher level facility, a level 1 exam is not going to be too much of a hardship or challenge for you. I would caution that, like when we talked about the primary clarifiers, the 4 zones. If you didn't review that material and someone on an exam asked you, what are the 4 zones of primary clarifier? Those 4, it's multiple choice exam question with 4 answers, and 2 of those answers are probably going to be really close together, and it could be quite easily to get those mixed up or turned around, or components of another. So it's really important to cover all this information. It sounded like a lot of this is refresher for most of you, which is awesome, because that allows us to get through the PowerPoints a little quicker and focus on review questions, focus on the practice exams. You may not have written an exam for a while, so it gives you the more practice time when questions and stuff and how they might be written are going to be important to you as well. So it's about 10 after. I'm not seeing any questions. I'm going to just throw it out there one more time. Any questions on the stuff we covered today? The next Thursday, we're diving right into the activated sludge section. It's going to be much more operations based for sure. What's probably a little more related to what's going on in your type of facilities. I'm going to ask one question before we go, just in preparation for next week. Is there anybody attending that does not operate some form of a secondary plant, whether it be BNR, SBR, mixed liquor tanks, even lagoon systems? Is there anybody that does not operate a secondary plant? So, okay, good. Thank you for that. We have one answer that there's at least one person or one group that does not operate a secondary plant. It's some good information for me to have just in preparation for this activated sludge section, to make sure that we touch on all the points. If you run a secondary plant, it's sometimes a lot easier to assimilate this information and process it. But if you we'll make sure that everything is covered in depth, because there definitely will be a chunk of that exam that's on secondary as well. Well, thank you everybody for this morning. Hopefully you found some good information. Make sure you spend some time reviewing the sections we covered today. Trickling filters, as you mentioned, you don't deal with, and there will be several questions on exams about trickling filters. So we want to make sure that that's prevalent in your mind. Okay. Thank you, everyone. Enjoy the rest of your day. It was nice chatting with you this morning.
Thank you, Mike, and thank you for another wonderful session. Thank you all for participating. Have a wonderful day.
Yes, take care.
All right. Tutorial number 3. That's the end of our tutorial number 3 with Mike Gosselin. Have a wonderful day. Bye.